Imagine this every time you order on Amazon, watch Netflix, or search on Google, data is being generated. But who makes sense of all that messy data? That's where data engineers come in. In today's video, we're going to break down data engineering from absolute scratch in a way that's easy to understand whether you are a beginner or already working with data. In this data engineering masterclass, you will learn data engineering workflow, OLTP versus OLAP databases, ETL pipelines, data warehouses and data layers, incremental loading, dimensional modeling, data lakes, data warehouses, lakehouse architecture, delta format, file formats, big data frameworks, cloud data engineering, medallion architecture, and much more. Why should you watch this video? The demand for data engineering is growing rapidly. If you want to be part of this domain, whether you're a business analyst, data analyst, or a complete beginner, this video is for you. You will learn every concept from scratch in a simple and practical way. In fact, you can expect at least 50% of your interview questions to come from these fundamental areas. So grab your notepad, pen or pencil and start taking notes because we are going to begin the data engineering masterclass now. Hi everyone, welcome to Product Tech Academy. I'm Imran Khan, a product leader with 20 plus years of experience in data engineering and product management. I've spent over a decade at Amazon managing data engineering and product initiatives. All right, so let's get started with our data engineering masterclass. This video is for anyone who has the excitement and passion to become a data engineer. In this masterclass, we'll cover every concept from scratch in a simple, practical, and easy to understand way. All you need is curiosity and a willingness to learn. So, why is this video for you? If you are looking to enter the data engineering domain, this will give you a strong foundation. If you're already a data engineer, it will help you strengthen your fundamentals because many professionals work in this field without complete clarity on core subjects. And if you already know these concepts, this is a great opportunity to revise and reinforce your understanding. In fact, around 50% of data engineering interview questions are based on these fundamentals. Once you go through each section with focus, you will gain the confidence to learn any new tools and technologies in this space. So, without wasting any time, let's get started. First of all, the most common question, what is data engineering? This is probably the first thing on your mind right now. What exactly is data engineering? If you're a beginner, you might feel like you don't know anything about it yet, and that's completely fine. In this session, we're going to understand everything from scratch, step by step. We'll start by answering what data engineering really is, and then move on to an equally important question, why do we need data engineers? Because today, companies are actively looking for data engineers, and the demand is growing rapidly. That itself gives us a strong hint about how important this field has become. So let's dive in and understand it in a simple and practical way. What is data engineering? Data engineering is all about building systems that collect, store, and prepare data so others can use it. Now, think of it like this: if data is raw ingredients, then data engineers are the ones who clean, process, and organize it into something useful. Now, let's go one step deeper. What exactly does a in data engineer do? They design and manage the data pipeline, the journey data takes from source to insights. That includes collecting the data from apps, websites, and APIs, cleaning and transforming it, storing it in databases or warehouses, and making it accessible for analysts and business teams. So, without data engineers, data is just noise. Why do we need data engineers? The equivalent question. Every company today runs on data, but raw data is messy, scattered, and often useless in its original form. Now think of it like this. If data is raw vegetables, then data engineers are the chefs who clean, cut, and prepare it into a ready to serve dish. Now let's make it more practical. What problems do this actually solve? Without data engineers, data is spread across multiple systems. It's inconsistent and unreliable. Reports take hours or even days. Decisions are based on incomplete or wrong data. With data engineers, data is centralized and organized. It's clean, accurate, and ready to use. Real-time dashboards become possible. Business can make faster and smarter decisions. Now we have discussed what data engineering is and why we need data engineers. So let's jump into the data engineering workflow. This is the right time to understand how everything actually works end to end. Let's start with the big picture of data engineering. No matter how complex system becomes, everything fits into a simple flow. In this workflow, we mainly have three stages: data production, data transformation, data survey. First, let's understand data production. This is where data is generated. Think about all the sources around you. When you open an app, when you scroll Instagram, when you place an order on Amazon, when you make a payment, every action creates raw data. This data can come from applications, websites, mobile apps, databases, APIs, and sensors. Example. Let's take a simple example: Amazon order. When you search for a product, click on an item, add to cart, place an order, all of this generates events and logs. At this stage, data is unstructured, messy, and high volume. It is not ready for analysis yet. Then next comes data transformation, core of data engineering, which is the most important part. Raw data is not useful directly. It has errors, duplicates, missing values, inconsistent formats. So what do data engineers do here? They clean the data, remove the duplicates, handle missing values, standardize formats, join data from multiple sources. This process is typically done using ETL pipelines, which is extract, get data from sources, then transform it, cleaning and processing it, load, store it in a system like a data warehouse. Let's continue this, say, Amazon example. Raw data might look like user ID, product clicks, payment logs, delivery updates. After transformation, you get structured data like total orders per day, revenue per category, top selling products. This is where raw data becomes meaningful information. Finally, we have data serving. This is where data is made available for dashboards, reports, business teams, data scientists, machine learning models. For example, a business dashboard shows daily sales. A product team sees user engagement metrics. A recommended system suggests products. All of this depends on clean, transformed data. So if we simplify everything, data protection is raw data is created. Data transformation is where data is clean and processed. And data serving is where the data is used to drive decisions. So far, we have understood what data engineering is and how the workflow looks. Now, let's see how this actually works in the real world. It all starts with data generation. Let me start with a simple question. How many of you checked your phone today? Opened Instagram, booked a cab, or made a payment? Almost everyone, right? And here's the interesting part: every single action you just did generated data. Every data system starts somewhere, and that starting point is data generation. See this API icon. Think of APIs as messengers working behind the scenes. Example: you open Paytm, check balance. Paytm requests data from your bank. Bank responds via API. Data is generated and exchanged instantly. Now look at this laptop. Every click you make, every page you visit, even how long you stay, everything is tracked as data. Have you ever searched for something? Then ads follow you everywhere. That's your data being captured. Now, this is the biggest one. You are the data generator. Likes, comments, reels, uploads. This is unstructured data, messy but extremely valuable. Example: Netflix recommendations, Instagram feed, all powered by your data. Now look at this cylinder. This is where all data is stored, and we mainly have SQL, which is structured in the form of tables and rows. NoSQL, which is flexible in the form of JSON, logs, and media. Think SQL is like Excel, NoSQL can be anything. So in one line, every click, every app, every interaction generates data. So now we have seen how data is generated. But let me ask you something. Can we directly use raw data for analysis? No. Let's move to the next step, data transformation. This is the most important step in data engineering. Data transformation, where raw data becomes useful. First, understand the problem. Raw data is unorganized, missing values, duplicates, different formats. Basically, chaos. Have you ever opened an Excel file and felt completely lost? That's raw data. So, what do we do first? We clean the data, remove duplicates, handle missing values, standardize formats. Example, India, IND, and India in small letters. Should this be three values or one? Exactly, we have to standardize it into one. Step two, structuring it. Now this the data is clean but still not fully useful. So we structure it in the form of creating new columns, apply business logics. Example, date of birth or age. Which one is easier for analysis? Date of birth or age? Age, because it's ready to use. Step 3, filtering. Now comes an important question. Do we need all the data? No, we filter it. Example, 1 million records only last 30 days. Relevant data, faster insights. Now look at the result. Clean, structure, ready to use. Let's make this real. Think about Swiggy or Zomato. Raw data, orders, delivery time, ratings. After transformation, it's average delivery time, top restaurants, customer insights. Now this is something the business can actually use. Transformation turns raw data into business value. So now we have clean, structured data, but here's the real question. What's the use of data if no one can access it? So now let's move to the final step, data serving. This is where data actually starts creating impact. Until now, we were preparing the data. Now we start using it. Data serving. This is where what turns data into decisions. Now imagine this is scenario. You have done all the hard work, you cleaned the data, you structured it properly, perfect data set is ready, but it's just sitting it in one database. Now think from a business perspective. A manager wants a dashboard. A data scientist wants data for a model. An app needs real-time recommendation. Can all of them directly go and query the database? Would you allow that? No, you shouldn't. Because it will be too slow, too messy, all honestly risky. So, what do we do instead? We don't give raw data, we serve the data in the right way, at the right time, to the right people. Now, let's see how this actually works in real life. Different people need data in different ways. Business teams, they don't want tables, they want dashboards. So, we use tools like Power BI or Tableau, where they see KPIs, trends, reports. App need data instantly, so we use APIs to serve real-time data like recommendation. And then data scientists, they need clean data sets for training machine learning models. Let's make this super real. Think about Amazon. When you open Amazon, you see recommended products, trending items, your order history. Do you think Amazon is showing you raw data database tables? Of course not. This is served data designed for you. So remember this. Data serving is what turns data into decisions. So if I bring everything together now, Data is generated from your actions. It is transformed into something meaningful, and finally, it is served for real world use cases. And as data engineers, you're not just moving data, you're not just cleaning data, you're building systems. That's power entire business. So now we are serving data to different users. But where is this data actually coming from? And where is it going? That's where upstream and downstream systems come in. Let me ask you something. When we say data pipeline, do you think it's only about tools and code? Or is it also about people? The truth is, it's both. In every data system, we divide things into two parts, upstream and downstream. Let's start with upstream. This is where data is coming from, APIs, applications, databases. But here's something important. Upstreams is not just systems, it's also teams. These are usually backend developers, product teams, source system owners, and your relationship with them is critical. Let me ask you, if upstream sends you bad data, can you fix everything? No, exactly. So, what should you do as a data engineer? You need to collaborate early, understand data sources, clarify data formats, agree on schemas, handle changes, that is, schema evolution. Don't just consume data. Partner with upstream teams. Now look at the center. That's you. You're not just writing pipelines. You're the bridge between upstream and downstream. Now let's move to downstream. This is where data is used. Dashboards, reports, and machine learning. But again, this is also about people. These are usually business analysts, data scientists, stakeholders. Let me ask you, if you build a perfect data set, but it doesn't answer business questions, is it useful? No, exactly. So, what should you do? Understand the business need, what metrics matter, what format they need, how frequently do they need data. Don't just deliver data, deliver usable data. So now think about this. Upstream gives you data, downstream consumes your data, and you're in the middle, managing both relationships. A good data engineer builds pipelines. A great data engineer builds relationship. But now comes an important question. Do upstream use the same type of systems? Not really. Let's understand that using OLTP and OLAP. But now comes an important question. Do all systems handle data in the same way? Not really. And to understand this, we need to understand two words, OLTP and OLAP. Let's take something we all use, a banking app. When you send money, that's a transaction. When you check your monthly report, that's analysis. Same systems, two completely different purposes. Let's start with OLTP, online transaction processing. This is where day-to-day data transaction happens. Insert, update, delete. Fast, real-time, highly reliable. Quick question. If your payment takes 2 minutes instead of 2 seconds, will you be happy? No. That's why OLTP systems are optimized for speed. Now, here's something very important. OLTP systems are primarily managed by DBAs, database administrators, and their focus is performance, data consistency, transactions never fail. But as data engineers, don't ignore OLTP. You need to understand it well. Why? Because this is your source of truth. This is where your data is coming from. Now, how do DBAs design OLTP systems? Using relationship modeling and a concept called normalization. The goal here is removing redundancy, ensuring consistency. Quick breakdown. 1NF, no repeating values. 2NF, full dependency on primary key. 3NF, no indirect dependency. All this ensures clean and efficient transactions. Some popular OLTP systems you will hear about: MySQL, PostgreSQL, Oracle, SQL Server. OLTP equals fast transactions plus highly normalized plus DBA manage. Now let's move to OLAP, online analytical processing. This is where analysis happens. Let me ask you, if a company wants to analyze 2 years of data, is it simple or complex? Complex, exactly. What OLAP does? Reports, trends, aggregations, business insights, heavy queries on large data. Now, this is where you come in. OLAP systems are typically managed by data engineers. Your responsibilities: building data pipelines, designing data warehouses, optimizing queries, ensuring data availability. You're responsible for making data usable by for the business. Now, here's a key difference. In OLAP, we don't strictly normalize data. We often denormalize it. Why? To make queries faster. Popular OLAP systems: Snowflake, Amazon Redshift, Google BigQuery, Azure Synapse. Let me simplify everything. OLTP, running the business. OLAP, understanding the business. OLTP, managed by DBAs, focus on transaction, highly normalized. On the other hand, OLAP, managed by data engineers, focus on analytics, often denormalized. So remember this, DBAs keep the system running. Data engineers make the data useful. And if you want to grow as a data engineer, don't just learn OLAP, understand OLTP as well. So now we clearly understand OLTP handles transactions, OLAP handles analysis. But the real question is, how does data actually move from OLTP to OLAP? Because they don't directly talk to each other. And that's where this comes in, ETL. ETL is the bridge between OLTP and OLAP. ETL stands for extract, transform, load. Let's start with extract. Where are we extracting the data from? OLTP, exactly. That is databases, APIs, applications. This is your source data. Now comes the most important part, transform. This is where you come in as a data engineer, cleaning the data, joining data sets, applying business logic. This is where raw data becomes meaningful. And finally, load. Where are we loading this data? OLAP, correct, into data warehouses. Now data is ready for analysis. ETL is what turns operational data into analytical data. So now our data has reached OLAP. But tell me honestly, do you think this data directly goes into dashboards? Some of you might say yes, but in real world systems, it doesn't work like that. Let's think like engineers for a moment. If raw data directly goes into dashboards, what could go wrong? Exactly. Errors, inconsistencies, wrong insights. So to avoid all this, we introduce layers inside the data warehouse. And this is where things get interesting. Let's start with this side. Staging. This is like a landing zone. Think of like this, where when you download a file from the internet, do you use it immediately or check it first? You check it, right? That's exactly what staging is. All data we extract first comes and sits here. But here's the key point. This data is not permanent. We call it transient data. It's temporary. It can be replaced, even deleted. Now tell me, why do we keep it temporary? Because we don't trust raw data yet. Now, once the data is cleaned and validated, where it should go? Exactly, into the core layer. This is the heart of your data warehouse. And here, data is stored permanently. We call it persistent data. Think of it like this: staging equals your workspace slash draft, core your final submission. Now, a very important question: why can't we directly load data into core? Let's break it. What if data has errors? What if the pipeline fails halfway? What if you need to reload yesterday's data? That's why staging exists. Staging gives you control, core gives you reliability. Staging where you question the data, core you where you trust the data. Now let's connect this full journey. Data is created in OLTP, moved and processed using ETL, stored and analyzed in OLAP, organized inside warehouse layers. And as data engineers, you're not just moving data, you're deciding where data can be trusted. So now we have data in our data warehouse, clean structure sitting in core. But here's the challenge. How do we load data every day efficiently? Let me ask you, if your table has 10 million records, every day will you reload all 10 million? No, right? And that's exactly why we use incremental loading. Instead of loading everything, we only load what is new or what has changed. Let's do a quick example. Yesterday, 1 million records. Today, 10,000 new records. So, how much should we load? 10,000. Exactly. So, now look at this flow. Data comes into staging and then moves into core, but only the incremental data moves forward. Now, tell me, what happens if we don't use incremental loading? We'll face slow pipelines, high cost, unnecessary processing. Think of your phone. When apps update, do they reinstall the entire app? No, only updates. That's incremental loading. Efficient pipelines don't move all data, they move only the required data. So now we know how data is loaded efficiently. But here's the next challenge. How do we design this data as business users can easily use it? And that's where dimensional modeling comes in. Let me ask you something. If I give you 20 tables, will analysis be easy or confusing? Confusing, exactly. So instead of complexity, we simplify the structure using something called a star schema. Let's start from the center. This is the fact table. This contains numbers, examples, sales, revenue, quantity. Quick question. Can business decisions happen without numbers? No. Now look around. These are dimension tables. They give meaning to your numbers. Example, customer, product, time, location. Let's say I tell you sales 1 lakh. Is that enough? No. You will ask which product, which city, which time. That's dimension. Fact equals numbers, dimensions equal context. Why do we call it star? Because it looks like a star, but more importantly, it makes querying simple and fast. Good data modeling doesn't store data, it makes data easy to use. So now connect everything. Data comes from OLTP, loaded efficiently using incremental loading, stored in warehouse layers, designed using dimensional modeling. And this is what makes a data pipeline scalable, efficient, business ready. So now we understood the star schema. Fact in the center, dimensions around it. But let me challenge you a bit. Is star always the best design? Imagine your company has millions of records. Same country name repeated, same category repeated. Is that efficient? That's where things start to change. We move from star to something more structured. Snowflake schema. What difference do you notice here? Exactly. Dimensions are no longer flat, they are broken into smaller tables. In star, one dimension equals everything. In Snowflake, we normalize dimensions. Let's take a product dimension. In star, product, category, subcategory, all in one table. In Snowflake, product table, category table, subcategory table. Now think like engineers. Why would we split this? Because it reduces redundancy, improves data integrity, easier maintenance. But nothing is free. More tables equals more joins equals slightly slower queries. So where would we use Snowflake? As large enterprise systems where storage optimization matters. To summarize, star equals speed, Snowflake equals structure. Now we designed our data beautifully, but real world data doesn't stay the same. Customers change, products change. So how do we handle that? That's where SCD comes in, slowly changing dimensions. Think about your own life for a second. Have you ever changed your city, changed your phone number, changed your address? Now imagine this. Your system actually keeps track of all your past data, your old city, your previous address, everything. Would that be useful? Yes or no? Yes, exactly. Because history matters, because data keeps changing over time. And that's exactly what we solve using slowly changing dimensions, SCD. SCD is all about handling changes in data, but not all changes are treated the same. That's why we have different types. Let's start simple. Type 0, no change allowed. Can your date of birth change? No, exactly. So once stored, we never update it. Whenever you have this kind of data, that's where we use SCD type 0. Type 0 means write once, never touch. Now let's move to type 1. Here we simply overwrite old data. Let's say your name is stored as Raj or WG. You correct it to Raj RAG. Do we care about the old typo? No. So we replace it. Old value is gone. Means type 1 is just to fix mistakes, no history needed. Now this is most important one. Type 2, where full history maintained. Let's go back to our example. You lived in Mumbai, moved to Bangalore. Now think like a business. If I analyze last year data, should it show Mumbai or Bangalore? It should show Mumbai because that's where you were at that time. So what do? We don't overwrite, we don't delete, we add a new record. So let me explain this in a simple way. Earlier the customer was in Mumbai, so we store the record with the start date and end date. For example, Mumbai, start date Jan 1st, end date March 31st. Now the customer moves to Bangalore. So instead of changing the old record, we add a new record. Bangalore start date April 1st, end date null because they are still there. So what did we do here? We didn't delete the past. We didn't overwrite it. We preserved history and added the new state. Now tell me, can we track customer journey over time? Yes. Can we do trend analysis? Can we audit past data? Yes. Type 2 is not just storing data, it's storing history. It's like time travel for your data. Now let's move to type 3. Here we store limited history. We create columns like current city, previous city, current city equals Bangalore, previous city equals Mumbai. Can we track 5 years of history here? No, exactly. Only limited history. Means type 3 is kind of a short memory, not full history. Alright, let's make this fun. Let's see how many of you got this right. No change allowed. Which type? Type 0, correct. You just want to fix the incorrect data. No history. Which type? Type 1, exactly. Now business says, I want full history, everything. Then which type? Type 2, perfect. And finally, I only care about the last value. Which type? Type 3, spot on. If you got all of them right, you already understood one of the most important concepts in data engineering. So now we have seen how structured data works. We modeled it, we handled changes. But let me challenge you. What about data like logs, images, videos, real-time streaming data? Can we fit all of this neatly into tables? Yes or no? No, exactly, we can't. That's where things get interesting. Let me ask you something. Where do you think Netflix stores all its videos? Millions of hours of content. Do you think it's sitting in rows and columns? Not really. That's where data lake comes in. Data lake is a place where we store everything. Structured data, yes. Semi-structured data, yes. Unstructured data, yes. No restrictions. Let's check your understanding. Logs, data lake, yes. Images, data lake, yes. Streaming data, data lake, yes. Exactly. Everything goes into the lake. Now look at the ecosystem. Data is coming from everywhere. IoT devices, applications, cloud systems, big data platforms, and all of it flows into one place. That is data lake. Now let me ask you something. What's the difference between a data warehouse and a data lake? Anybody? Simple. Data warehouse is clean, process, ready to use data, whereas data lake is raw, flexible, anything goes. So now tell me, is raw data useful for business? No, exactly. It needs processing, transformation, cleaning. Think of it like this. Data lake is raw vegetables, whereas data warehouse is like cooked food. You can't eat raw vegetable directly. You need to process them. But there's a catch. If you don't manage your data lake properly, it turns into data swamp, which means you have data but no idea what's inside. Data lake stores everything, but value comes only after processing. So now connect the full picture. Modeling, which is star Snowflake schema, changes. This is done through SCD, and the storage is the data lake. Let me summarize. Data engineering is not just pipelines. It's decision, design choices, and trade-offs. So now we understand what a data lake is. It stores everything. Raw data, flexible, highly scalable. But let me ask you something. If I take this raw data and give it directly to a business team, can they actually use it? No, exactly. They can't. Because raw data is messy, unstructured, and not ready for decision making. And that's why we don't rely only on data lakes. We also need data warehouses. Let's make this real. Think about Amazon. Every click you make, every order, every review, every image. Where does all this data go first? Data lake. Correct. Now imagine the business teams ask, what are the top selling products last month? Do we go and query raw logs for that? No, exactly. That's where a data warehouse comes in. Let's simplify this. Think of it like this. Data lake equals storage layer, data warehouse equals business layer. Data lake stores all types of data, raw format, highly flexible, whereas data warehouse only structured data cleaned and processed, optimized for reporting and analysis. Quick check. Which one is better for dashboards? Warehouse, correct. Which one is cheaper for storage, storing large volumes of data? Lake, exactly. Now, here's an important concept. Data lake follows something called schema on read, meaning we decide structure later. Data warehouse follows schema on write, meaning structure is defined before storing data. Let's take a simple example. A CSV file comes into the data lake, no strict structure, just stored as is. But the same data in a data warehouse goes into proper columns, validated, cleaned, and structured. Data lake equals store first, understand later, whereas data warehouse equals understand first and then store. Now is the interesting part. Data lake is flexible, data warehouse is structured, but maintaining both can be complex and expensive. So, what if we could combine the best of both worlds? That's exactly where Lakehouse comes in. So, here's the real question. We just compared data lake and data warehouse. One is flexible, the other is structured. So, why are we maintaining two separate systems? Isn't there a way to get both flexibility and structure in one place? And that's exactly where Lakehouse comes in. Lakehouse is a modern data architecture that combines the best of both worlds. You get flexibility of a data lake, performance of a data warehouse. In simple terms, it's like having raw data and business ready data in the same system. Let's look at how things worked earlier. Earlier, data lake was mainly used to store raw data and data warehouse was used for reporting analysis, which means we had to move data from the lake to the warehouse, build separate pipelines, maintain separate storage systems, more movement, more cost, more complexity. Now with Lakehouse, the same data can be used for reporting, analytics, machine learning. One data, multiple use cases. Quick question. Do we still need to move data again and again between systems? No, exactly. That reduces duplication, reduces cost, and improves performance. Let's take a real world example. Think about Netflix. They have user activity logs, video streaming data, recommendations. Earlier, raw data in lake moved to warehouse, then used. Now with Lakehouse, same data can directly power recommendations, dashboards, analytics. Means faster insights, fewer pipelines. But here's the important part. Lakehouse is not just an idea. It works because of modern technologies. Things like column-based file formats, transaction layers, data versioning. This makes raw data reliable and query ready. Lakehouse equals flexibility plus performance without duplication. So now the question is, how does Lakehouse actually achieve this? How can raw data behave like structured data? The answer lies in file formats and storage designs. Let's understand that next. Let's think about this. If I ask you to calculate total sales, do you really need customer name, address, phone number, everything? No, exactly. So why should the system read unnecessary data? Now, this is where storage design becomes important. There are two main ways data is stored, row based and column based. In row based storage, data is stored record by record. Everything in one row stays together. This works really well for transactions. Think about a banking system. When you make a transaction, the system needs complete information. So row-based storage works perfectly. Now let's look at column-based storage. Here, data is stored column by column instead of reading full rows. We read only what we need. If I want total revenue, I only read the revenue column, not customer name, not address, which makes it much faster. So tell me, which one is better for analytics? Column, exactly. Row based, optimized for writing and transactions. Column based, optimized for reading and analytics. Now, here's where things get even more interesting. Modern data systems don't just store data, they store it intelligently using specialized file formats. And two of the most important formats you will hear are Parquet and Delta. Let's start with Parquet. Parquet is a column-based file format, which means it is designed specifically for analytics. It helps in reducing storage, improving query performance. Imagine a table with 10 columns. If you need only one column, Parquet reads just that column instead of scanning everything. That's a huge performance gain. But here's the limitation. What happens when data changes? If you need to update data or delete something, Parquet alone doesn't handle this very well. So we introduce something more powerful, Delta. Delta is basically Parquet plus a transaction layer on top. It brings versioning, asset transactions, data reliability. In simple terms, it makes your data safe and manageable. Now look at how it works. Data is still stored at Parquet files, but every change is recorded in a transaction log. So instead of changing data directly, we create new versions. Version 1, update. Version 2, delete. Nothing is lost. Now tell me, if someone deletes data by mistake, can we recover it? Yes, exactly. That's called time travel. Delta makes data lakes reliable, and that's what enables a lakehouse architecture. So now let's connect the full picture. Data lake stores everything. Data warehouse gives structured insights. Lakehouse combines both. File formats improve performance. Delta adds reliability. Data engineering is no longer just about storing data, it's about designing systems that are fast, efficient, and reliable. Because in the end, the real power is not in the data, it's how you design and use it. So far, we have built a strong understanding of how data engineering works end to end. And this is part A of the data engineering masterclass. In part B, we will continue this journey and move into more advanced real world concepts. In this part A, we have covered data engineering workflow, OLTP versus OLAP, ETL pipelines, data warehousing and data layers, incremental loading, dimensional modeling, data lakes, data warehouses, and modern file formats like Tilta and Parquet. That's a strong and comprehensive understanding. And now in part B, we take it to the next level. In part B of this data engineering masterclass, we will focus on more practical and advanced concepts. We will cover Lakehouse architecture, big data framework, cloud data engineering, and Medallion architecture. And most importantly, we'll explore the two most widely used platforms, AWS and Azure. So, if you're serious about becoming a data engineer, part B is where everything starts to come together. And there's a lot more coming your way. We'll also be bringing you exciting tutorials on AWS, Python, SQL, product management, and agentic AI. If you found this valuable, subscribe to the Product Tech Academy channel, like this video, and share it with someone who wants to grow their tech career. Thanks for being part of Product Tech Academy, and I'll see you in part B of the Data Engineering Masterclass.